Hello, welcome to this introductory session of Star CCM Plus, where I will teach you how to use the software. In this first session, we will be making a 2D simulation of a wing. You can follow along and press pause if I'm going too fast, but I will try to explain as many of the steps that I'm doing. So if you have any questions, you can always send me an email afterwards. If something was unclear, feel free to contact me. I will put my email at the end. So first, to start, all you're going to need is Star CCM Plus, and I will be using one step file of a wing. This is a file I created in Inventor, and I recommend you do the same. It is also possible to import points into Star CCM itself, but the process is easier in my opinion when you just import step files you created in another program. So for starters, you first need to create a 3D CAD model. So you right click here and create new. It'll open this this environment where you can import parts and you can manipulate them. So for starters, you will need to right click here and import CAD model. Then select the CAD model you desire. For example, I will use this one. Right now it'll be imported, and there is one very important part when doing 2D simulations. When you are working in Star CCM, it'll only do the 2D simulation if the part you're simulating is on the Z plane. So this XY plane here is the Z plane, the Z equals 0 plane, and your part needs to be right on it. So I designed my parts in my software in the way that it automatically is there, but if you're importing points, make sure you draw those points on this Z equals 0 plane and then extrude from there. Next up, we are going to be creating the domain in which we will be simulating. So to do this easily, you can select the plane, the Z is equals 0 plane, and you can click to create sketch. It is quite easy. You select and you pull, and then to easily edit it, you can select these corners and just change up their coordinates. Now, the part we are simulating is about 12 centimeters in length and about 10 to 15 times that in distance from each edge is enough to simulate this part. So I'll be putting this at 1.5 meters that way and minus 1.5 that way, and this one I will be putting at minus 1.5 that way, and at 1.5 that way. So right now we've got this domain, and you can go ahead and create it, and now you'll have this sketch, and you can click on extrude, and you can just extrude it in the correct direction, of course. So I'll extrude for 0.2 one way, and where do I select the direction? Yes, I'm sorry, reverse. All right, and then very important, actually one of the most important is no body interactions. Otherwise it would merge itself with the wing we've already put here, and then they would be one body, and that of course would not be ideal. So you go ahead and create that, and perfect. So first off, we're going to rename things. So renaming things is, you do that by pressing F2, and that way you can easily rename things. And That way everything remains clear. These names will be carried on throughout the process and to the derived parts from it. That way you can easily identify the things you are using. The next step we need to do is to name these faces. So you can select faces by pressing Control and, oh, that's not a face. Here we go. And you are going to grab these. Come on, yeah, thank you. All right, and then you're going to right click on them and click on rename. So these three will be our inlet. All right, then right at the back will be our outlet. All right. Then it's also important that this face is different from this face, so we're just going to rename it. Their name doesn't really matter. You can just rename it 1 and 2. Rename. All right, that way when you look at them here, you can see that these are all have separate names. All right, and in the same way, I will do it for, hang on a second. I'm going to make this transparent. Hide. All right. In the same way, I'm going to turn this into wing. All right, and I'm also going to add an angle of attack variable parameter to this. So to do that, you right-click the wing and you go to transform. And the transformation we want to do is a rotation transformation. All right. Now, this will rotate around the the z-axis. Now, I also designed my wing in SolidWorks so that its leading edge is on this z-axis. This also removes a bunch of work for me. Otherwise, I would have to select another axis for it to turn around. But in this case, it removes all this work. Now, I wanted to turn in the other direction actually, so I am going to change the axis direction to a -1, all right? And I am going to, by clicking here, expose this as a parameter. And I'm going to call this wing AOA, angle of attack. That way it'll show itself in my program later and I won't have to come back here to edit it. So right now we're going to leave it at 0 degrees. Okay, so right now I think we are done here in the 3D CAD, so I will close it right here. And now we're back into our main interface, and right now we need to prepare these parts we just created and make sure that they can be simulated. So first we go to this 3D CAD model here and we create a new geometry part. I'm sorry, I think I need to do it. Yes, this is what I need to do. I need to select these both and create new geometry part. This will transform them from their CAD systems into a body of triangles, and it is necessary to simulate them. So next up, we are going to create a subtract from these two parts we just created. So what is a subtract? It is a Boolean operation that we input both the domain and the wing, and as target we take the domain. And what this is going to do is going to remove this wing from this domain, and in that way we'll be left with a cutout of our wing in the domain, be sure to press cat boolean, otherwise it doesn't work. And that way. And now we still need to press execute, or it won't actually create it. And Star CCM doesn't actually have any visual uh, things by themselves, but you can create them, and it's very important that you learn to do it, because otherwise you will always be working blind, and it's important to check your work. So always you can just create these scenes. Now I'm going to create an empty scene, and I'm going to drag my subtract into it, and I'm going to make sure that it has a surface displayer and an outline displayer. Okay, and as you can see right here, it has indeed created, this is the subject I just created, and it is indeed my domain with a cutout from the wing I put in. Now, the next step is to another operation, and you're going to do a meshing operation, and you're going to badge for 2D meshing. So you're going to click here, and you're going to click on this subtract, and you okay, and you execute it. This is where your program will create problems for you if you didn't align your parts with the z plane, z equals 0 plane. And if you did it correctly, then you can see here that there is a small red dot around the subtract. That means you did it correctly. Now, next operation is again a meshing operation, where we are going to create an automated 2D mesh. I'm going to click the subtract, and you're going to have to select your measures. So quadrilateral measures make squares, triangular measures make triangles, and polygonal measure makes polygons like hexagons and pentagons and everything. Personally, I recommend the quadrilateral measure, as it is in general the best, and certainly when there is a dominant wind direction. And of course, don't forget the prism layer measure. I will explain its usefulness later when we get to meshing. All right, for now I'm just going to leave this here. I'm going to do a couple extra preparations, and then we will get back to this mesh. So before we get to meshing, a couple important things need to happen. So from this subtract, we want to first create our regions. So you go to assign parts for region, and very important is to select the subtract and to create a boundary for each part's surface. To apply, close, and now here you have your region with your boundaries. Now, it seems I accidentally created this into two different. Of course, it doesn't really matter. They're both walls, but in general, you this should be one part, but it doesn't really matter. Indeed, it just they will both be walls. But first, so we have this inlet that we need to edit, and you need to change its setting to be a velocity inlet. All right, so these will be velocity inlets, and this one, the outlet, you go to edit, you go to pressure outlet. All right, so this is a pressure outlet, this is a velocity inlet, and these are both walls. Even though these should be one part, it doesn't really matter that they're two parts right now. I must have done something wrong back in the 3D CAD model, but it won't impact the results. So now we've created the regions, we can go to the Continua tab and create a new physics continuum. Now here we will have to select models, and from this we will select two-dimensional, steady, gas, as we're using a gas, segregated flow, and you will be using constant density, as there is no compression at this speed, as we're well within the incompressible. The flow we will be looking at will be turbulent, and very important here, the type of turbulence model we will be using is the K omega 1, as it is the one that is best suited to flow separation and near wall applications. So the system automatically selects any of the recommended ones you need. This is all we need for now. So we press close, then we go back to this boundary, and we have this inlet where we can now change the physics conditions. Now you can, for example, we want this to be a velocity inlet, and we will select a constant velocity of 15 meters per second. And you have to change the flow direction. So the flow direction specification is not boundary normal because there are 3. Otherwise, it would be an input through here, an input through here, and an input through here. That's not what we want. What we want is to change it in components, and that way it must have added, yes, flow direction constant, and then we have this value here. Now the x-axis is in this direction, but we want it in the opposite direction. That is why we will put a minus here, and voila. That will set our initial conditions, not our initial conditions, I'm sorry. This is the ongoing conditions. So now through this, there will be a velocity of 15 meters per second being pushed through. Now, of course, to speed up the simulation, we can also set initial conditions. Now, initial conditions is the conditions that are before you start the simulation. So, very important, you can press this velocity and go to a constant, and we will set this to minus, we could set it to 15, but in general, putting it a bit lower creates a slightly more efficient system where your simulation will converge a little faster. So we go to minus 14 meters per second. That will add the initial conditions. So now that all the preparatory work has been done, we will get to one of the most important parts, and that is the meshing. So to have the program mesh, you can either right click here and click execute, or you can click here, this button, it will execute all the meshing. Now, as I've said earlier, there is no automatic visualization, so you need to create a scene, new mesh scene, and that is the mesh scene. Now, as you all can see, this is a terrible mesh. There is absolutely no detail, so we're going to edit these things a bit so that the wing and everything is properly represented in this. So first we can start by just lowering the base size. The base size is currently 1 meter, which is ridiculously large. We will go to 5 centimeters as a base size. Even just changing this will already greatly improve the the quality of our mesh. But very important also is that there's these big parts here on the side that we don't really care about. I mean, we do care about them, but they don't need to be as finely represented as the parts around here. So we will go to custom controls, new, and then you go to curve control. No, not curve control. You go to surface control. You have surface control, you edit this, and you apply this to the inlet and the outlet. Enter. And you add the target surface size, you add a custom to this. You can also edit other things, but those are not necessary right here. So for now, we will close this, and when you go here, you can have values, and you can edit it relative to base. I'm going to edit this to be about 300 times the base size. That way, when I mesh it, you can see that this is nice and smooth, and there's no reason to have detail over here. The actual details we want are here. Now, let's look at this wing. Now, this is still clearly not enough detail. These are very sharp corners, and this is very, very much not desired. So we're going to create the same thing. We're going to create a new surface control. We're going to edit, and we're going to put the wing part and the default part. Yes, that is because I wrongly combined them. Usually you should only add one, but this will indeed add this part to it. And the custom controls we will be using is the target surface size we will give a custom, the minimum surface size we will give a custom, the surface curvature will also be given something special. And for now, we will also give it wake refinement, which I will show you immediately how that works. So, yes. All right. So the target surface size, I'm sorry, I'm in the wrong thing. This is the values. So the target surface size, I will take about 50% of it. The minimum surface size, I will take 5% of it. The surface curvature, so the surface curvature actually is what it does actually, it makes it so that when a full circle is done, the minimum amount of cells is this. Now, as you can see, this is much too low here. We need more detail around this curve. So what we're going to do is going to increase this to about 80. And then finally, wake refinement. That is what this is going to do is this is going to add additional detail in a certain direction that we're going to specify right here. So the size is the percentage of base we're going to use is also 50. And the wake refinement, that is just the growth rate. Hang on. I'm sorry, it's right here. You're going to have to edit. So of course, 10 meters is way too much. We only need about 0.75 meters of extra detail in the direction of -1. And the spread angle will actually increase the angle of the refinement. So that way we can use 0.15 radians. And all right, we'll already look at the difference that this is going to make. Okay, that is better, but still not good. So I'm going to just lower the base size a bit further. 2.2. The nice part is that all of these other things are compared to this base size. So by lowering this base size, I will increase the detail of everything that is happening. Right, this already looks much better. Now, another very, very important thing is the prism layer controls. Now, prism layer controls will add a small layer of prisms, which will be very useful in determining the boundary layer that is going around this. So I'll go to edit, and all right. Now, what is important? The number of prism layers. You can make sure that they're actually 10. Actually, 10 is mostly good. The stretching is not really that important. The concave angle limit is also not important, I think. And then there's the prism layer total thickness, also related to base. I think that is actually quite okay currently. I will look at whether that is still the case. All right. This actually looks fine, but we still have an issue right here at the end. This is unwanted and can be fixed quite simply. I will look up how. All right, so I found what fixes this. You can fix this by increasing the minimum thickness percentage of your prism layers. So this is the percentage of the thickness where it will decide to stop making prism layers, but you can change that to 1, and that way when you remesh it, you can see that this prism layer will go all the way around it. All right, and that way you will still have a proper simulation around your trailing edge. Now, I'm quite still unhappy with this curvature, so I'm going to increase the curvature control here to 160, I think, and the minimum surface size to 2.5. That way, I think this will lead to a smoother leading edge, at least. All right, yes, that is already better. Still not perfect, but of course we want to save on computing space, and this is a good compromise. Now, there's a couple things that we need to visualize before, and one of those is y plus. Now, y plus is a value that is used to determine whether your boundary layer is properly being simulated. For this, for the k omega turbulence model, this value needs to be between 1 and 5 to be correctly. It can be lower. There is no problem in that. So I will now show you how to visualize this. So to visualize this, we need to create a scene, and you will make a new scalar scene, and it'll be shown up right here. Now, there will be a function block here, and you can change that to wall y plus. All right. You can go to this scalar scene, scalar, and then you still need to edit it and make sure that in the parts here, that the actual thing that is being used is the wing. I'm selecting both because I split it on accident, but there you go. Close. Now, I've already run something, so you shouldn't see this, but this should still be white. Once you run the simulation, there will be values over here, and you'll be able to check whether your y plus values are correct or not. Now, these y plus values, I'm not going to explain what they are. These will be further elaborated on by Theo in his more theoretical course, and also Professor Hoeneckers in his course about CFD2 will also correctly explain these. All you need to know for now is that the value needs to be below 5 and above 1. It can be lower than 1, but then it's not really necessary. All right. Next, there's a couple other scenes we're going to make. We're going to make a vector scene. Oh, that is, I'm going to just clear the solutions I had already tested, just that way you can properly see. So there is this vector scene. I'm going to rename it to the speed scene. That way you can make sure it's in these, it automatically selected the velocity already. All right, perfect. Then all I'm going to do is edit, and that is very important. It does not need to be glyph, but line integral convolution. This will smoothen it out and show a way prettier visual. All right, then I'm going to rename the scalar scene really quick to the y plus scene. All right, and then I'm also going to add one more scalar scene, and I'm going to call this the pressure scene. All right, so edit. Nope, that's not necessary. Here you're going to select a function, and you're going to select pressure. All right, so now the scenes are created. You can switch between them here. These will help you visualize the things that you are simulating. But there's still actually a few numerical things that need to happen, and that is why we're going to be creating reports and monitors. These are used to report and monitor on anything that is happening during the simulation. So firstly, we're going to create a few just very simple reports. The first one we're going to create is a downforce plot. going to name this down force. Yes, edit. And so what you're going to do is, of course, it's in Newton, and you need to select the proper direction. The direction is 0, -1, because it's the minus y direction that we are interested in. Voila. Then I'm going to copy it really quickly. I'm going to make a drag force, and this one also needs to be edited, and make sure that it is 0 and -1 as well. Oh, I forgot to add the selected parts to it, so I will do that here, and I will do the same. Edit parts here and here. All right. It is important that this is applied, otherwise you will not be calculating anything. These need to be applied to a certain object. All right. From these reports, I can do create monitor and plot from report. Yes, single plot. I mean, you can choose one plot per, but I prefer to have them on the same plot. So I down force and drag report. Yes. I'm sorry, plot. Plot. All right. Now I can also create a I'm not sure how to do this again. I think it is expression. Edit. All right, yes, that is how we do it. So what you will be doing right now is I'm going to get the lift to drag ratio of this wing. And so what I need now is these two reports. Downforce divided down, yes, downforce divided by drag force. Okay, and I'm going to lift to drag, create monitor and plot from report, lift to drag monitor plot. Yes. All right, so we should be ready now to actually run this thing. So right now I am going to open these scenes just in half screens. That way you can watch them more closely. This is the speed scene. I'm going to write the pressure scene right there. And I'm going to, the Y plus scene is also rather important. All right, and here will be our monitors to read. So firstly, what are we going to do? We're going to initialize the solution. I'm sorry, not initialize the solution. No, yes, it is initialize the solution. This will add the initial conditions. So as you can see, the velocity is currently 14 meters all across. I'm going to add to the stopping criteria. I'm going to set this to 3000. It should be stabilized before that, but that way we can see. And once I hit start, it's going to open the residuals plot also, which is showing us what the residuals are. All right. So what you currently can see is that the simulation is running. It's running quite fast, actually. And what we're waiting for currently is for the for these residuals to converge. So for them to become really small and for them to become a constant value. As you can see, hang on a second, here is the lift to drag monitor. It is doing the same, it is stabilizing, and probably similarly the downforce and drag plot is also doing just that. All right. Everything is looking quite stable currently. So I will stop it right here. All right. So, a couple things that we can check and control. So firstly, there is the wall Y plus. Now, as you can see from this thing, this shows, oh, it doesn't get the numbers bigger, but it clearly shows that along this entire thing, the wall Y plus value is never exceeding 5, which is correct, and that way we can ensure that the boundary layer has been properly simulated. Right here, this is a velocity graph showing the velocities around our wing, and here is the pressure graph showing the different pressures around our wing in a similar way. Now, here you have the drag and downforce. You can read these values, and here you have the lift to drag. Now, most importantly is to check the residuals. The residuals need to be stable. So these are stable residuals. They all have reached really small values, and this is also telling us that this is a steady simulation. There is no variation in time anymore. If we keep this running, the results will not change. Sometimes your residuals will have a sort of wavy, periodic character. That is also okay if you check Y, of course. Sometimes it's simple vortex shedding over here, or things like that. Now, what is also very important is that I'm going to show you now is that I'm just going to clear this solution. All right, so now we're back to this. I'm going to show you where you can change this parameter that we made. So when you go into 3D CAD model and you go into the design parameters, you can see that this wing AOA, which we added earlier, is still there. When I edit this thing to, for example, 10 degrees, and I press remesh, it's going to reapply it, and if we did everything correctly, yes, it edited it throughout the entire thing, and I don't need to change anything. I can just repress initialize solution, and I can run it again. And this is extremely useful, meaning you can do it quite efficiently. And when you've done this correctly, you can also, this is all you need to do to set up later, what do you call it, design manager studies, which allow you to iteratively test a lot of things. So as you can see here, this simulation has much uglier residuals, but they are periodic at least. And they are at least behaving in a periodic way, which is also to be seen in our lift to drag monitor and also to be seen in our downforce and drag plot. You might be wondering where it's getting these values. Since this is a 2D simulation, there shouldn't be any forces. These forces come from Star CCM extruding this wing in the z direction for 1 meter. So the downforce you're getting here in reading is in Newton per meter of wing. So the value you're reading here is if this wing was 1 meter long, it would be producing this much downforce. Now, these values are quite tough to read, obviously. So what we're going to do is we're going to create some average reports. So to create this, we create statistic reports. I'm going to edit it to average downforce edit. You take the mean of the last n samples. In this case, we will take the last 1,000 samples, since we had a length of 3,000, and you can clearly see that it is having a periodic behavior in the last n samples of a monitor, and that monitor is the downforce monitor, I think. Yes, exactly. Close. All right, I'm going to copy it, and then I'm going to average drag force, edit this to, all right, drag force monitor. Yes. I'm going to create a monitor plot of them. Single plot, average, drag, and average downforce and drag. All right. So this now will be the average, just so I'm going to clear the solution and reinitialize it and rerun it. So as you can see, these values are now smooth. It doesn't change the actual values that they're happening, but this creates a much more readable value. You don't have to do any calculations afterwards. But you should still take into account that the potential values are fluctuating, since that is actually a bit worse than if they were just constant. But I mean, vortex shedding is something that is sometimes unavoidable, and it's just the way it is. So it's still quite useful to have these averaged values. Also, just for clarity, having these scenes open here actually does slow down the simulation process. So if I were to just remove these, I'm sorry, I do still need the, where they are, there, the residuals. So as you can see, the simulation is going much faster if I just leave everything closed. So we will be really done in no time now, and then we can check at the end what the values are. Now it can still be useful when you're doing some new things, in to have a one-to-one view of what you're doing and to see if the flow is going correctly. If you're getting weird residual values, then you can check what might be going on in the speed scene and in the pressure scene. But as you can see here, you can still watch them. And hang on, where's this plot? The average downforce plot is right here, and the average drag force is right there. Put this at 0. So that way you can watch these. Know that this is a 2D simulation, so it's actually quite simplified. If this value is in Newton per meter of wing, but you can really expect these values to be, the downforce can be a bit lower, about 80% of what this is, because it's 2D simulation, and the drag force will also be significantly higher, not 3 times as high maybe, but if you do this simulation in 3D, the drag force will be higher than what it calculates over here, due to the fact that turbulence is an inherently 3D phenomenon, and this just assumes that this is a single strip, and it just doesn't add any turbulence in the third dimension, and everything just flows parallel very smoothly. So do take that into account when you're doing 2D simulations. These run extremely fast, as you can just see. This took maybe 30 seconds to run. And it's while some 3D simulations can take hours to run just to get one result like this, just to do like maybe 1,000, 2,000 iterations. So the speed is definitely the advantage of this, certainly when you're optimizing things and changing things, and testing just the characteristics of your wing profiles. It's very useful for that. But do know that 2D simulations are actually quite simplified compared to regular 3D simulations. All right, so lastly, there is one extra thing that we can do to check the accuracy of this simulation, and that is to make sure that it is mesh independent. So currently, we're right here, we're getting a average downforce of 30 and a average drag force of 2. If this was a good simulation, then increasing the mesh's decreasing the mesh's size, so increasing the amount of cells, should not impact this result. So if I change this base size from to 1, so that is a mesh that is half as big, so it will be twice as fine over here. Of course, this takes longer to create. It'll be 4 times as many cells, also 4 times as much computing power, so this will take quite longer, but still not too long, of course. So once this is done, I will run it, and all right, finished, clear solution, initialize, and I will remove this, and I will run it now. Now, as you can see, this is still running quite fast, but significantly slower than the other simulation, of course. But as you can see, we are still averaging out at about the same values as our previous simulation. This is good news, of course, but hold on a second. We'll wait till this is done. And the thing is that you need to compare these values in the end. If they are significantly different, then there might be something wrong. You might need to refine your mesh even more. If they are similar, then good job. Then you probably did a good job of getting it. Here we're seeing quite some, I mean, not any difference in the downforce department, but we're seeing some difference in the drag force, not by a terrible amount, about 10%, but it might be worth running this one once again even a little bit more fine to see if that has an impact. So I'll clear the solution. I'll change my base size once again to 0.5. Hang on a second. What you can also see here is that how it reacts when it gets more fine. I'll remesh this once again. Now it's going to take even longer, but it is okay, as the result is accuracy, of course. All right, this seems to be taking a little bit longer. Oh, it's done, but I will still get back to you once this simulation is finished. All right, it's almost done running, but it's quite comfortably running. It's almost done, it's getting there. But the values have quite, I wouldn't say converged, but they are periodic and well behaved. Here you can still see this periodicity is due to this rhythmic vortex shedding that is happening over here. It is the same always, but it definitely does have an impact on the wing. This is not behavior that you want to have. So consider if we lowered this this wing's angle of attack, this behavior would go away, of course. So, but it is something to consider when you are producing. Also, this when you're creating your parts, this will adversely affect any aerodynamic parts that are behind it, of course. So that is also when if you're making the front wing or anything, do consider that. Do consider the air that you are releasing behind you. All right, so it's done running. It now got 32 and 1.9, which are once again different values. So I might need to refine it even more. All right, I will get back to you when that is done. Okay, so with a few more refinements and a few more mesh optimizations, including like refining this leading edge even further. I was able to get some converging results. These are the final results that we get, independent of the mesh. Of course, if you get too coarse, the results will change again. But that kind of concludes our first lesson for now. This was just a very simple introduction to how to use the program. Next week, I will make a lesson 2 where I will teach you guys how to do more complex parameters and do more complex simulations, also still 2D. And I will teach you how to use the design manager to use to make large batches of simulations, and that way to find an optimal setup to your things. All right, feel free to contact me. I will put my email in the description, and that's it. Thank you very much.